Imagine if we could empty the oceans, letting the water drain away to reveal the secrets of the seafloor.
Hidden deep beneath the waves of the Western Pacific lies the Marianas Trench, the deepest point of all the oceans.
Using the latest underwater scanning technology, piercing the deep oceans and turning accurate data into 3D images.
5,000 meters. That's not just a number. That's the distance between you and a world so alien, so hostile, so utterly unlike anything on the surface of this planet that sending anything down there, let alone something designed to think, was considered one of the most audacious scientific gambles of the decade.
Special models, drop cams equipped with digital video cameras and powerful flashlights to explore the deepest places of the ocean.
No sunlight has ever touched the seafloor at that depth. The pressure would crush a steel drum like a paper cup. The temperature hovers just above freezing. Communication with the surface takes seconds per signal, seconds that, in an autonomous mission, are an eternity. And yet, a team of scientists sent something down there that had never been attempted before. Not a human, not a standard probe tethered to a ship by a cable. An AI-powered autonomous drone built to see, to adapt, and to make decisions entirely on its own. What it found has forced researchers to rewrite assumptions that have stood for decades about the deep ocean, about the origin of life, about what is and isn't possible in the darkest corners of our own planet. Stay with me, because this story builds in ways that are genuinely difficult to believe, and every single part of it is real.
Could these extremophiles hold secrets to life's origins?
The mission that nobody thought would change everything. To understand why what this drone found matters so profoundly, you first need to understand what it was actually sent down to do, because the answer is almost embarrassingly mundane compared to what it discovered. This was supposed to be a mapping mission, a joint research effort involving oceanographic institutions across 3 continents, targeted one of the least explored regions on Earth, the Clarion-Clipperton Zone, a vast abyssal plain stretching 4.5 million square kilometers between Hawaii and Mexico. To put that in perspective, that's roughly half the size of the continental United States, sitting at the bottom of the Pacific Ocean, largely uncharted, largely invisible to science. Previous expeditions into this region had used conventional tools: remote-operated vehicles tethered to ships by cables, basic seafloor landers dropped from the surface. The technology was tried and tested, but it had fundamental limitations. A tethered vehicle can only go where the cable allows. A remote-operated vehicle can only look where a human operator thinks to point it. In a region covering millions of square kilometers, that is the scientific equivalent of searching a continent with a single flashlight. The AI drone was designed to be something categorically different. It had been trained on thousands of hours of deep-sea footage, geological surveys, and biological data from previous expeditions. Its machine learning systems could identify anomalies, shapes, patterns, signals, chemical compositions, faster than any human observer sitting at a monitor on a ship 5 kilometers above. And critically, it didn't need to wait for instructions. It didn't need a cable. It could decide independently where to turn, where to hover, and where to look twice. Scientists called it the first truly autonomous deep ocean intelligence mission. The research team expected to come back with better maps, detailed sediment profiles, a more accurate picture of what the Clarion-Clipperton Zone's seafloor actually looks like at resolution no previous technology could achieve. They got all of that. And then the drone found something nobody had put in the mission brief. I want to ask you something right here, right now, before we go any further. When you send an intelligence, even an artificial one, into a completely unexplored environment and tell it to flag anything unusual, what do you think happens when it flags something that doesn't fit any existing scientific model? What does a research team do when their own technology returns data that contradicts everything they thought they knew? We're about to find out.
This 50-centimeter long miniature drone that is no larger than a briefcase draws inspiration from the movement patterns.
The moment the drone stopped, the drone's first pass over the seafloor was, by all accounts, completely routine. Rocky sediment, the scattered potato-shaped mineral formations known as polymetallic nodules, lumpy, dark, ranging from the size of a golf ball to a grapefruit, littering the seafloor across vast stretches of the Clarion-Clipperton Zone. Strange, slow-moving deep-sea creatures drifting through the blackness. Familiar species, expected formations. The models predicted all of it, and all of it showed up exactly as predicted. And then the AI stopped, not with an alarm, not with a flashing warning light, not with any dramatic signal to the surface team. The drone simply paused its forward trajectory, hovered, and redirected its sensor array toward a patch of seafloor approximately 30 meters wide. Then it did it again, and again. According to the mission logs, by the time the surface research team noticed the drone's behavior, it had repeated this same hover and redirect sequence 4 times in the same location. The AI had independently decided 4 separate times without any human instruction that this particular patch of ocean floor warranted sustained, close-range attention. When the researchers pulled the raw data from those 4 passes, they found it, an electrical signal, faint, steady, consistent, and entirely unexplained. The seafloor was generating voltage. Let that land for a moment. An inanimate patch of ocean floor, 5,000 meters beneath the surface, sitting in total darkness with zero sunlight, zero biological activity visible to the sensors, was producing a measurable, consistent electrical current. Not a spike, not interference. A low-level sustained signal rising from the mineral nodules on the seabed. The research team's first instinct was to dismiss it as instrument error. At that depth, equipment behaves in ways that can confuse even experienced oceanographers. Pressure distorts metal housings in ways that can affect readings. Near-freezing temperatures affect circuitry. Salt water, corrosive, conductive, relentless, finds every microscopic gap in a housing seal. Anomalous sensor readings at 5,000 meters are not unusual, they are expected. But the AI drone had been engineered with redundant sensor arrays, specifically to rule out instrument error. Multiple independent systems, all reading the same environment simultaneously. And every single one of them was reporting the same thing: a real, measurable, sustained electrical current, rising from the seafloor. The researchers had no model for this, no existing framework into which this reading comfortably fit, and the drone, operating on its own machine intelligence, had already flagged it as significant long before any human thought to question it.
The study says it is also capable of underwater experiments and efficient deep-sea tasks like collecting marine samples from the seabed.
Dark oxygen, the discovery that rewrites biology. Here's where the story shifts from interesting to genuinely world-altering. The research team didn't stop at confirming the electrical signal. They kept asking the next question. If voltage is being generated by these mineral nodules, what is that voltage doing? The answer, when it came together from the drone's chemical sensor data, stopped the team cold. The current, microscopic, low-level, but real, was strong enough to perform a process called electrolysis, the splitting of water molecules, H2O, 2 hydrogen atoms bonded to 1 oxygen atom, being pulled apart at the molecular level by the electrical charge emanating from the nodules. The hydrogen and oxygen were being separated, and the oxygen was being released into the surrounding water at 5,000 meters depth, in total darkness, with zero sunlight, zero photosynthesis, no living organisms anywhere in the immediate environment that could account for it. The AI drone had just confirmed a process that, until this mission, was considered essentially impossible. The geochemical production of oxygen in conditions that every biological and chemical model said were incompatible with oxygen generation. Researchers gave it a name: dark oxygen. A completely non-biological geochemical process producing breathable gas in the deep ocean. Quietly, steadily, with no sunlight, no life required, no mechanism that anyone had previously described or predicted. I need you to sit with what that actually means. Every model of Earth's oxygen cycle places photosynthesis at the center. Plants, algae, cyanobacteria, living organisms using sunlight to produce oxygen as a byproduct. That's the story. That's the system. The deep ocean, by definition, was considered a sink for oxygen, not a source of it. Water absorbs oxygen from the surface, carries it downward. Nothing down there was thought to generate it. This discovery does not just add a footnote to that model. It punches a hole through one of its foundational assumptions. If oxygen is being produced geochemically at the seafloor, by mineral chemistry, by pressure, by the interaction of metallic nodules with seawater, then the deep ocean ecosystem has had access to a resource that none of our models accounted for. Life down there may be doing things we haven't yet observed, sustained by processes we didn't know existed. We already knew that life had found extraordinary ways to survive in the deep ocean. Near hydrothermal vents, cracks in the seafloor where superheated water erupts, carrying dissolved minerals, entire ecosystems thrive in complete darkness, using chemical energy instead of sunlight. Tube worms, chemosynthetic bacteria, shrimp with no eyes, life that rewrote the rules about what environments can support biology. But this is different. Hydrothermal vent ecosystems use chemical energy. This is oxygen, the specific molecule that powers the metabolic processes of virtually every complex life form on Earth's surface. If dark oxygen production is widespread across the Clarion-Clipperton Zone, the deep ocean's capacity to support complex life is fundamentally larger than we thought. Here's the question I want to throw to you. We've spent decades assuming the deep ocean is a biological desert compared to surface waters. What happens to every model of marine biodiversity, every ecosystem calculation, every understanding of how life distributes itself across this planet if that assumption turns out to be wrong? Tell me your thoughts in the comments, because the scientists working on this data are asking exactly the same question.
It's been an exciting occupation because you're on the cutting edge of science, new discoveries all the time.
The implications for alien life. Now the story leaves Earth entirely, and this is where it gets truly extraordinary. The moment the dark oxygen data was confirmed and circulated among the research community, a separate community of scientists took immediate notice. Not oceanographers, not marine biologists, astrobiologists. Scientists whose professional focus is the search for life beyond Earth. Here's why. Europa is one of Jupiter's moons. Beneath its thick crust of ice, kilometers of frozen surface, sits a vast liquid ocean. Scientists have suspected this for decades based on gravitational data and the behavior of Europa's surface. But Europa receives almost no direct sunlight. Its ocean floor is rocky and mineral-rich. And until now, the prevailing scientific consensus was that the absence of sunlight made the likelihood of complex life there extremely low. The dark oxygen discovery changed that calculation. If a mineral-rich seafloor can generate oxygen geochemically, without sunlight, without life, just through chemistry and pressure, then Europa's ocean floor may be doing exactly the same thing. The conditions aren't just compatible with this process, they're arguably ideal for it. Now extend that logic to Enceladus, one of Saturn's moons. Enceladus has geysers. Enormous plumes of water vapor erupt through cracks in its icy surface and shoot hundreds of kilometers into space. That only happens if there is liquid water below the ice, heated from beneath. Scientists believe Enceladus has a liquid ocean, a rocky seafloor, and active hydrothermal processes. And now we know that mineral-rich seafloors can produce oxygen in the dark. The implications for the search for extraterrestrial life did not shift because we found something in space. They shifted because an AI drone found something 5,000 meters under our own ocean, something we had been sitting above for the entire history of human civilization without ever knowing it was there. Think about that for a second. The discovery that most advances our understanding of where life might exist in the solar system wasn't made by a space telescope. It wasn't made by a Mars rover. It was made by an autonomous AI navigating total darkness at the bottom of the Pacific Ocean, finding something that every previous expedition had missed. What else is down there? What else are we sitting on top of, completely oblivious to?
Throughout most of recorded history, men had just assumed that beyond a certain level the sea was pretty flat, pretty dead, fairly lifeless.
The patterns in the seafloor. But the drone hadn't finished. As its survey continued, as the surface team began processing the dark oxygen data and trying to construct a framework that could accommodate what they'd found, the AI flagged something else. Something that, by the account of the researchers who reviewed the footage, was even harder to explain than the electrical signal. Geometric patterns, not the random, irregular formations of natural sediment, not the chaotic shapes of erosion or tectonic movement, not the biological structures of coral or sponge colonies. Near-perfect mathematical structures pressed into the seafloor, spirals, grids, tessellated ridges following precise, repeating angles, the kind of geometry that, on the surface of the Earth, would immediately prompt questions about human involvement, the kind of regularity that the natural world, under most circumstances, simply does not produce. The AI drone had been trained extensively to distinguish natural geological formations from anomalies. It had processed thousands of hours of seafloor imagery across multiple oceanic regions, learning the full range of what natural deep-sea geology looks like. And it had flagged these patterns, not once, not twice, but repeatedly, as anomalies, as things that did not fit its model of natural formation. The surface team reviewed the time-stamped footage frame by frame, and then they found something that sent the room into silence. The patterns were changing, slowly, almost imperceptibly, slowly, but changing nonetheless. Ridges extending incrementally, spirals tightening with a precision that looked almost mechanical. The structures were not static. The seafloor was in some kind of motion, not the sudden dramatic shift of tectonic activity, not the gentle drift of underwater currents. None of the sensors detected any of those forces operating in that location. But the electromagnetic sensors detected something else. Tiny fluctuations in the local magnetic field, synchronized with each incremental shift in the seafloor patterns. When a ridge extended by a measurable amount, there was a corresponding ripple in the electromagnetic data. When a spiral tightened, the magnetic reading moved in concert, shape and energy, changing together, synchronized, consistent, repeating. Now I want to ask you something directly, and I want you to be honest with yourself. If you are a scientist sitting in a research station looking at this data, an electrical signal you can't explain, oxygen being produced in total darkness, and now geometric patterns in the seafloor that appear to be actively, dynamically changing in synchronization with electromagnetic fluctuations, what is the first question that forms in your mind? Because for the researchers on this mission, according to the logs, that question hung in the room for a very long time before anyone spoke. The lead researchers, when they eventually described their conclusions publicly, were careful with their language. Deliberate, measured. Scientists trained to resist dramatic overstatement, particularly when the data is unprecedented. But they used a specific word that is worth paying close attention to. They called it a system, not a reaction, not an anomaly, not a geological quirk. A system, an ongoing, stable, self-sustaining process that had almost certainly been running for thousands of years, entirely undetected, under 5 kilometers of Pacific Ocean. Shape, energy, chemistry, synchronized, sustained, unknown. Nobody had a model for this. Nobody had predicted it. Nobody had described it in any paper, any textbook, any existing framework of deep-sea science. The AI drone went down with instructions to map a seafloor. It came back with evidence of a process, complex, dynamic, and ancient, that science had never seen before.
But now, a Chinese team has developed a small robot that can operate in the world's deepest sea trench under extremely high pressure.
The mining crisis. The stakes just became existential. Now comes the part of this story that transforms it from a scientific discovery into an urgent global crisis. Because the polymetallic nodules at the center of everything the drone found, the nodules generating the electrical current, enabling dark oxygen production, and apparently influencing the dynamic structure of the seafloor itself. Those nodules are not sitting untouched and protected in a scientific sanctuary. They are the primary target of the global deep-sea mining industry. The Clarion-Clipperton Zone, the exact region where the AI drone made these discoveries, holds the most commercially significant concentration of polymetallic nodules on the planet. They are extraordinarily rich in cobalt, nickel, copper, and manganese. They are sitting on the ocean floor, accessible, extractable, and extraordinarily valuable. And they are valuable not for some abstract industrial reason. They are valuable because of the energy transition, because every electric vehicle battery, every large-scale renewable energy storage system, every solar panel component, every wind turbine requires these metals. The world has committed to a transition away from fossil fuels, and the mineral supply chain that transition depends on runs through the deep ocean. Mining companies, major international corporations, already hold permits to begin extraction in the Clarion-Clipperton Zone. Regulatory frameworks have been under construction for years through the International Seabed Authority. Equipment is being designed and mobilized. The industry has been building toward this moment for over a decade. The plan, in its broadest terms, is to harvest polymetallic nodules from the seafloor by the millions of tons, vacuum them up, process them, feed them into the supply chain that powers the green economy. And now scientists working on the AI drone's data are asking a question that has the potential to bring that entire industry to a halt. If we remove the nodules, do we shut off a dark oxygen-producing system we don't yet understand? Think through the implications carefully. If these nodules are generating electrical currents that split water molecules and release oxygen into the deep ocean, and if that process has been sustaining deep-sea ecosystems for thousands of years in ways we are only beginning to map, then extracting those nodules doesn't just remove rocks from the seabed. It potentially collapses an oxygen production system that entire communities of deep-sea organisms may depend on. It destroys, permanently and irreversibly, an ecosystem we have barely begun to discover. And it eliminates the physical evidence, the nodules themselves, the patterns they are creating, the electromagnetic process they are driving. That might be our best scientific model for understanding how life first emerged on this planet in conditions before photosynthesis evolved. Here's the dimension that is almost too significant to absorb. If dark oxygen production is real, widespread, and ancient, and early evidence suggests it may be all three, then the deep ocean floor may have been producing oxygen long before photosynthetic life appeared on Earth's surface. These nodules, and the process they enable, might be a living window into the pre-biological chemistry of early Earth, a natural laboratory that has been running, undisturbed, for hundreds of millions of years, and we were about to vacuum it up to make EV batteries. I want to know what you think about this, because this is not a simple question. The green energy transition is real and necessary. The demand for these minerals is not going away. But the argument for pausing extraction to fully understand what we might be destroying is not a fringe scientific position. It is increasingly the mainstream one. Comment below. Do you think deep-sea mining should be halted until this process is fully understood? Or is the urgency of the energy transition too great to wait? This is a debate that is happening right now in scientific and policy circles, and your perspective matters.
People were probably astounded by what they were seeing because clearly the ocean floor had enormous changes in relief, was very mountainous in some places, had great deeps in other places.
What the AI saw that humans couldn't. There is one more dimension of this story that deserves serious attention, and it's not about the ocean. It's about the tool that made the discovery possible. Previous expeditions had visited the Clarion-Clipperton Zone. Human-operated remote vehicles had moved across this same seafloor on cables from ships. Conventional sensors had taken readings. Scientists had reviewed the data. And none of them found this. Not the electrical signal, not the dark oxygen production, not the geometric patterns, not the electromagnetic synchronization. The same seafloor, the same nodules, the same process, running for thousands of years, and every previous human-led expedition missed it entirely. The AI drone found it because it was trained to notice what doesn't fit. It found it because it didn't have a human operator's assumptions about what was worth looking at. It found it because when it encountered an anomalous reading at that patch of seafloor, it had the autonomy to stop, hover, redirect, and look again, 4 times, without waiting for permission. A human operator, receiving that first anomalous reading from a tethered ROV, might have logged it and moved on, might have attributed it to instrument noise, might have had 100 kilometers of seafloor still to cover that day and no cable slack left to investigate. The AI was not constrained by any of those factors. It simply decided the anomaly was worth investigating until it understood it. There is a profound lesson here about what artificial intelligence can do in scientific exploration that human-operated tools cannot. Not because the AI is smarter, but because it is patient in a way humans and human systems are not. It can flag an anomaly, sit with it, return to it, and refuse to discard it simply because it doesn't fit existing models. That refusal to discard the anomalous is exactly how paradigm-shifting science happens. And we have now built a tool that does it autonomously, in environments that no human can reach. The question that follows from that is one of the most important in the history of scientific exploration. What else has human limitation caused us to miss? What anomalies have been logged and dismissed on previous expeditions because a cable ran out, a shift ended, or a model said, "That's probably instrument error"? What is sitting in old expedition data sets, flagged as noise, waiting for a system patient and parameter-free enough to look at it properly? This discovery may be the beginning of a fundamentally new era of scientific inquiry, one where the bottleneck is no longer human presence. It's imagination.
We know very little about the species that live down there. We know very little about the distribution of the biological communities. We don't know how these animals have adapted to living under this unbelievable pressure that exists down there.
The bigger picture. What comes next? The immediate scientific response to the AI drone's findings has been exactly what you would expect when foundational assumptions get challenged. A mix of intense scrutiny, urgent replication efforts, and a growing recognition that the implications cannot be contained to a single discipline. Marine biologists are reworking their ecosystem models for the deep ocean. If dark oxygen is real and widespread, the distribution of life at abyssal depths may be radically different from what existing surveys have mapped. There may be organisms, communities, populations, entire species, sustaining themselves on this geochemically generated oxygen in regions that previous expeditions classified as largely barren. Geochemists are focused on the mechanism, trying to understand precisely how the mineral composition of the nodules interacts with deep-sea pressure and water chemistry to produce the observed electrical current. If the mechanism can be fully characterized, it opens theoretical possibilities that extend well beyond the ocean. geochemical oxygen production in mineral-rich environments under pressure could inform our understanding of planetary chemistry across the solar system. Astrobiologists, as we discussed, are already applying this framework to Europa and Enceladus, and likely to other ocean worlds being identified by ongoing space telescope surveys. The search for life beyond Earth has just gained a powerful new model. Policy researchers and international regulatory bodies face perhaps the most immediately urgent challenge. The International Seabed Authority, which governs deep-sea mining permissions, has been operating under a scientific understanding of the Clarion-Clipperton Zone that this discovery fundamentally revises. Existing permits were granted based on impact assessments that did not account for dark oxygen production, geochemically sustained ecosystems, or the dynamic electromagnetic processes the AI drone identified. Those assessments are now outdated. And the question of what happens to the mining industry while scientists race to understand what they've found is not merely academic. It involves billions of dollars in investment, the energy transition timeline of multiple major economies, and the well-being of ecosystems that have existed for hundreds of millions of years without any awareness that a species on the surface was about to start vacuuming them up. Final thoughts. Here is what we know. An AI-powered autonomous drone descended 5,000 meters into the Pacific Ocean on what was supposed to be a routine mapping mission. It identified an electrical signal that no previous expedition had detected. That signal led to the confirmation of dark oxygen, geochemical oxygen production in total darkness, without photosynthesis, without sunlight, without life. The same mission returned footage of geometric, dynamically changing patterns in the seafloor, synchronized with electromagnetic fluctuations that no existing scientific model had predicted. The mineral nodules at the center of this process are the primary target of the deep-sea mining industry, which holds active permits to begin extraction. The implications extend to marine biology, geochemistry, astrobiology, climate policy, and our most fundamental understanding of where life is possible in the universe. And we found all of it not by sending a human into the deep, but by building something intelligent enough to notice what we had been walking past, or rather sailing over, for the entire history of oceanographic research. I'll leave you with the question that the lead researchers on this mission said kept them up at night after the data came in. If a seafloor 5,000 meters below the surface of our own ocean, the planet we have been living on for all of human history, was capable of this, and we didn't know, what else don't we know? What other systems are running beneath us, beyond us, around us, that we haven't yet built the tools to see? The ocean is 71% of this planet's surface. We have mapped less than 25% of it in any meaningful detail. The drone found this on what was essentially its first serious autonomous mission into the abyss. We are at the very beginning of knowing what we don't know. That's the full picture as science currently understands it. And it is still evolving rapidly. I want to hear from you. Does the dark oxygen discovery change how you think about the deep-sea mining debate? Does it change how you think about the search for life beyond Earth? Are you more excited about AI as a scientific tool, or more unsettled by what it tells us we've been missing? Drop your thoughts in the comments. The best conversations on this channel happen right there, and I read everything. If this video changed the way you think about any of this, the deep ocean, AI exploration, astrobiology, mining policy, any of it, please give it a like. It makes a genuine difference to how far this story travels, and this is exactly the kind of story that deserves to travel as far as possible. Subscribe if you haven't, because the follow-up to this video goes into the specific organisms already being discovered in the Clarion-Clipperton Zone that nobody expected to find. And given everything we just covered, you will not want to miss what's down there. See you in the next one.